Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman, and I'm the Marketing Director here at the Academy. Today's webinar is titled Application of Artificial Intelligence Machine Learning for Engineering Solutions in the Water Sector. Our Executive Director, Dr. Daniel Other, will serve as a moderator and will introduce our speaker today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We'll do our best to address each question at the end of the presentation. Before we get started, Dr. Uther would like to say a few words. Dan, how are you doing?
Hi, Marissa. Hi, welcome everyone who's joining our webinar today. As many of you may be enjoying a lovely summer, you may be also looking for ways to upgrade your skills. And learning about artificial intelligence is all the rage. So today's webinar is an example of how the American Academy of Environmental Engineers and Scientists supports the leadership and excellence of our members. Today's webinar is one of a multi-part series on AI, and we're glad to have you joining us to hear about the applications of AI and machine learning for engineering solutions in the water sector. Before I introduce our speaker, Dr. Aryan Imani-Nejad from the Academy patron Black Veatch, let's all pause and take a moment to offer thanks to the patrons of our Academy. Patrons are firms and utilities, including those whose logos are listed on our screen right now, who financially support the Academy. When you speak with folks from these organizations, please say thanks for their support of Academy programming. It is in part through their generosity that we are able to bring today's event to our members at no additional cost. And today, we offer a special thanks to Black Veatch for their long-standing and continued support of Academy programming as a patron. If you have an interest joining as a patron, or if your organization has an interest in proposing or sponsoring a particular webinar, please reach out and let us know. Marissa and I are here to listen to your story and to help to match your needs with our available programming. And now on with today's webinar. Today, it's my privilege to introduce Dr. Aryan Imani-Nejad, who's employed as a data scientist, AI/ML engineer with Black Veatch. Aryan has a background in chemical engineering, and he holds an earned doctorate in civil and environmental engineering from the University of Illinois, Urbana. He's been intentional in his efforts to cultivate a comprehensive skill set tailored to the wastewater treatment sector. His expertise lies in process engineering and design, with practical experience in utilizing advanced wastewater modeling platforms such as GPSX and Sumo. During his graduate studies, which employed bioelectrical systems for real-time plant-wide carbon monitoring in water resource recovery facilities, Dr. Imani-Nejad earned his IBM Data Science Professional Certificate, gaining hands-on experience in web scraping, data wrangling, exploratory data analysis, and dashboard development using Plotly and Dash. All sound like very impressive terms. Driven by a passion for data science and predictive AI, Dr. Imani-Nejad is dedicated to advancing the integration of artificial intelligence and machine learning into environmental engineering, particularly within the domains of water and wastewater treatment. His distinctive combination of engineering knowledge, research experience, and industry-recognized certifications position him to make meaningful contributions to the development of sustainable and intelligent environmental solutions. As Aryan delivers his presentation today, I remind you that I have the privilege of moderating a question and answer event at the end of today's presentation. So it would be of great help if you would share your questions in the Q&A panel, and then we'll integrate those into today's discussion. And now with those introduction, Aryan, my friend, the stage is yours. We are so excited to hear from you. Thanks for joining us today.
Thank you so much for your kind introduction. I really appreciate it. So hello, everyone. I know we have close to 100 people attending our webinar today, and I want to say that I'm very grateful for your time, and I hope that today's session will be beneficial to all of us as attendees. So let's begin our talk. The focus of my presentation is going to be on the applications of AI and machine learning for engineering solutions in the water sector. And I have divided my presentation into two different sections. The first section is going to be a general conversation about AI and the general trends that AI has taken over the past couple of years. I want this to be a starting point for discussions today and future discussions. And the second section, we will go over two of the case studies that we have been working on at Black Veatch that focuses on using AI and machine learning to offer solutions to different facilities. So first section, the general section. Let's first talk about the pressures driving AI adoption and innovation in the water field. So the first and most important factor is that we have an aging infrastructure. A lot of the water and wastewater facilities across the US are decades old, and some of them are struggling to keep up with demand. And AI can come into play and help us with maintenance of our equipment and also prediction of our process efficiency so we can run our facilities in a much more efficient way. The second one is the workforce retirements. It's been a couple of years that we are going through a generational change in the workforce of our major facilities. And when you talk to a lot of these operators, they're extremely knowledgeable and extremely experienced. And when they get retired, that knowledge transfer can sometimes not happen as efficiently as possible. So there is going to be a knowledge gap between the older generation and the newer generation. And AI can come into play here and help us fill that knowledge gap and be able to transfer that knowledge more efficiently so we can run our utilities in a better way. And third is the regulatory complexity considerations, because a lot of these facilities, they're going through more and more stringent effluent quality limits. And in order to meet those effluent quality limits, they can use AI to make sure that they are running their processes as efficiently as possible, and they are within the discharge limits while also minimizing their resource use. So digital water in general offers some promises. The first one is the real-time monitoring and automation capabilities, which I think is the area where most of the AI products are being offered so far, and it's one of the most promising areas where we use AI and machine learning to continuously monitor different processes and also to respond instantly to operational changes. And it allows us to be very proactive when it comes to maintaining our processes and also maximizing the treatment efficacy. The second one is predictive maintenance, where we use AI to predict equipment failure. A lot of these AI models, they can pick up on different patterns that usually lead to failures in different equipment. And when we use these types of models, we can predict when an equipment failure is likely to happen and be proactive about it. So it basically transforms our maintenance practices from reactive to proactive, which allows us to be much more efficient with our resources. And another area where a lot of studies have come out and there's a lot of potential there is plant-wide cost savings. For example, in a wastewater treatment facility, if you're using chemicals to do certain things to make sure you're meeting your effluent discharge limits, you have two options. One is to potentially overuse your chemicals to make sure you're meeting your effluent discharge limits. And that comes at a cost. And the cost is you are potentially wasting too much money, or you are underutilizing your chemicals to make sure you're not wasting too much money and you are at a risk of not meeting your effluent discharge limits. So there's always a balance there where AI can come into play and create that balance to make sure that we are using as much chemicals as we need or as much oxygen as we need without overusing our supplies and also without risking discharge limit violations. But everything comes at a risk. And the major risk is, when it comes to digital water, is cybersecurity. Up until a few years ago, the general consensus was that cybersecurity was a major threat to only water treatment facilities because of the sensitivity that they had and not really wastewater utilities. But since a few years ago, where unfortunately some major attacks took place also on wastewater treatment facilities, now both sides are taking this very seriously for a good reason. So now we have a consensus that no matter if it's water or wastewater, cybersecurity is always a big issue. And there are practices that people take to make sure that these issues are taken into consideration. For example, you can use your AI systems just as advisory systems where they don't really have any direct control. They just suggest set points or advise your operators on the best practices. Or we can also use AI behind the plant's firewall and use them on very dedicated unit processes where it doesn't really control anything else other than that specific unit process. And also, so therefore, we are minimizing the risks that are involved. The second one is operational risk and expertise loss. I don't think this is an imminent threat, but it's something to be considered because if we over rely on AI and we get less hands-on experience with different aspects of operating a plant, that leads to a friction when it comes to gaining process knowledge. And that is something to consider. But again, I don't think this is an imminent risk, but it's something to consider where we're using AI. So we need to make sure that we are creating the perfect balance between hands-on experience and reliance on AI. And the third one are regulatory and ethical concerns. I think this mostly applies to large language models because a lot of the times when we're using large language models, the data that they use the data that was used to train them was probably someone else's work. So let's say, I don't think it's happening now, but let's say you're using a large language model to do design work. How ethical is that? Is it using data from other people's work? Or if you're making conscious decisions about using large language models, who makes those decisions? And so ethical concerns are something that need to be taken very seriously, especially if you're right now we're living at an age where large language models are finding more and more applications. So it's very important to take into consideration this aspect of digital risks. And so I also want to take a moment to talk about the AI spotlight. AI and machine learning have been around for decades, but if you've paid close attention to this field in general, you know that there's a lot more attention since a couple of years ago or a few years ago. And I've always been fascinated by it. When you think about it, there might be some contributing factors that have led to this sudden rise of AI in our normal conversations and day-to-day conversations, and also specifically in our field. So the first one is the lower barrier to entry. AI and machine learning frameworks now, since a few years ago, they are much more accessible, and they have moved away from those complex academic environments in the past to more user-friendly platforms. So that's one of the contributing factors. The next one is the availability of more user-friendly languages. I mean, if you have used MATLAB before for AI and machine learning, for example, MATLAB is extremely powerful in a lot of areas. It is still the dominant force when it comes to deployment. But when you compare MATLAB to Python, for example, you realize that it's not really, the syntax is not really as easy to learn. And so when all these amazing libraries and packages were introduced in Python that allow you to do relatively complex machine learning models with maybe a few lines of code or 10, 20 lines of code instead of writing 100 lines of code in MATLAB, that leads to more accessibility, and that leads to a more widespread adoption of these types of modeling strategies. The third one are novel machine learning algorithms. So until a couple of decades ago, artificial neural networks were around, and they were still getting used. But artificial neural networks are relatively complex to develop. They are very resource intensive, and they require a high level of expertise to make sure that the model is robust and well developed. But since maybe like a decade ago, a lot of focus had been dedicated towards more tree-based models that are much lighter. They are much easier to develop and maintain, and they also have relatively comparable performance to all these complex artificial neural networks. So that's also another reason why we see a sudden increase in the overall AI spotlight. And the last one, which I think is the most important one, that's why I'm highlighting it here, is the introduction of ChatGPT and large language models in general. I think potentially the main reason that we are hearing a lot about AI was the introduction of large language models back in 2022. And I mean, they were commercialized back in 2022. And since then, we have seen an amazing shift in the way that AI is involved in our lives. And I think that's potentially the most important reason why we get all this attention in AI. And because of that, I just want to talk about these large language models a little bit, just as a general conversation. So I am a power user of large language models. I use them for a variety of different tasks. Like last year, I used them to do my taxes. I don't recommend you doing that. It's just like work for my personal life. I use them to generate my training exercise plan for my weeks. I use them all the time. And when I do that, there are always like things that I consider when I'm interacting with these large language models. And the first two important ones are the data retention and the privacy considerations. These large language models, they store the data, and there's no way to ask them to remove the data that you have fed them. So it is really important to make sure that we are not really feeding any type of important data to these large language models, because they learn them and they will use that for future training, which is not ideal. And the next two are the security and the bias situations. So I see that a lot of organizations have already started rolling out Copilot, for example, because most organizations already have subscriptions to Microsoft products, and they have started rolling out Copilot, which is an amazing tool. You can use it in every single Microsoft product, and it allows you to do a lot more work in a lot shorter amount of time. So when the data is sensitive, it is important to try to stick to large language products that are offered as an organizational tool instead of you going to the general common ones that are available out there. And then the last one is the bias situation, which I think is very important. I mean, large language models have a tendency to create an echo chamber. The way you ask the question will heavily impact the way they will generate the response. For example, if you go to any large language model now and you ask it, what are the benefits of drinking coffee on eyesight? That gives you a relative a response that is dedicated to proving that there are benefits to drinking coffee to your eyesight. But if you go around and ask it, are there any proven benefits and any proven relationship between drinking coffee and using drinking coffee and eyesight, you will get a different response. So it's very important to take that into consideration when you're dealing with large language models in your day-to-day life or in your professional work. So when we're using that, there are some common pitfalls and best practices that happen. So the most common pitfalls are being uncritical of AI responses, a lack of citation verification, and also an overconfidence in AI-generated content. One of the worst things that can happen is if somebody copies and pastes whatever response all these AI models generates into either their student work or in the professional work. It's really bad, so we need to be careful not to do that at all, and also do our due diligence on the responses that they generate. And the best practices are always cross-reference all this information with the trusted sources. A lot of these newer models, they give you the link, so always go there and check the link. And also verify the facts before incorporating them into work. And always remember that AI responses are good starting points. They give you a good structure over whatever you're trying to do, but they are not final products. And that brings us to this argument of augmentation versus replacement. Sometimes I see over promises when it comes to large language models and people saying that it's going to replace human expertise, but I don't think that is the case. These large language models, they're really good at processing vast amounts of information and generating initial drafts and prototypes and automating routine cognitive tasks. I will tell you why I highlighted cognitive there. But when it comes to interactions with humans, human expertise is still required to make sure that that domain-specific knowledge is included in any type of interaction, and that contextual and nuanced understanding of any problem that is involved, that is still not replaced by these large language models. And of course, the ethical decision-making. AI and large language models do not really have any ethical decision-making built into them. I mean, to some point, they do now, but it's not nearly as close to the human aspect of it. And so related to cognitive tasks, I came across this study, which was very fascinating and a little bit scary. This came out just a couple of weeks ago, back in June, and it's a study that was done at MIT. And what they did here was they came up with a essay writing task, and they had three different groups of people. One group was solely relying on large language models, the ones on the left. One group was using internet search and also their own brain capacity to try to do that task. And also one group was using only their brain, nothing else. And what they realized was there was a significant drop in neuron connection and brain activity in the people who were only using large language models compared to the people who were using their brain only. And you can see that here, the people who were using their brain only, they had much more significant neuron connections compared to the people who were using large language models. And another interesting finding that they had is In the second stage of the study, they asked all those large language models to only use their brain, and they asked all those people who were only using their brain to start using large language models. And what they observed was that the group that was only relying on large language models, their brain activity stayed low, even when they were using only their brain. And the ones that were using only their brain activity stayed higher when they were using large language models. So it was an early evidence of a potentially medium to long-term effect of relying only on large language models. The study mentions that they have their limitations, so I encourage you to go there and read it yourself. But I think it's a very fascinating and I would say scary time for people who are just only relying on large language models. So I just wanted to bring this to your attention too. And then one other thing, I know we also have students attending this session. I wanted to include this in our general discussion too. I've been fortunate enough to be invited to be reviewers for several journals to review the AI ML submissions. And what I see way more often than not are papers that have very robust methodologies or the how problem here. But the why problem or the motivation behind this study is not really clear. A lot of times it feels like it's somebody who has a hammer and everything looks like a nail to them. The question is, okay, so why did you use AI, all these advanced and complicated machine learning models? Why did you use a neural network? Why not a simpler model? Or why not a mechanistic model? I always say if you have access to a good mechanistic model, you should use that. You shouldn't just go directly to AI. So if you're a student and you're getting started or you're trying to publish in this area, I would strongly recommend that you spend a good amount of time to try to come up with a good reasoning and a good why instead of just focusing on the how part and the methodology. And so if you're in that area, this is a paper that was published by Zhu et al. Came out from Dr. Ren's research group. It's an amazing paper that outlines really well the common pitfalls of using environmental data sets in AI and machine learning research. And it provides a very comprehensive list of recommended actions to try to overcome those pitfalls and make sure that the machine learning models that we're developing are robust and they align well with the common characteristics of environmental data sets. So if you are a student active in this area, I highly recommend you reading this paper. I have included a link here. And finally, this is my last slide for the general conversation. This is a question that I keep asking myself, and I think about it a lot. Is there going to be an iPhone plateau for AI? When you look at the progression of iPhone technology, the first generation was okay, and then iPhone 6 and 7 was big advancements. iPhone 10 everyone was like, wow. But iPhone 11, 12, 13, 14, 15, they all pretty much look the same, and they offer very similar capabilities. A new year comes out and they upgrade the base storage and like, thanks. But it's just the amount of innovation that is going into these products have kind of plateaued. And it's one of the questions that I keep asking myself, are we going to see a plateau of that kind in AI innovation and AI field in general? And it's just something to be seen. I don't think we're nearly close to that. Especially for the water wastewater sector, we are just taking baby steps now, and we have a lot more work to do. But in general, I think it's something. It's a good point to consider when we're talking about AI in general, and just keeping a close eye on the direction that this field is taking in general. So that was my last slide. If you have any questions on the first part, we can take that now. If not, we can move on to the second part. I'm just going to take some water.
Well, let's go ahead. We can discuss just a little bit, a couple of questions on this first part. We've got some in the, I reminded people in the chat, et cetera. So just to ask you a couple of questions to follow up on this, right? So really loved that you talked about some of the bias and some of the issues of the ethics. So here's one to speculate on, right? Like these large language models, whether it's Chat or Gemini or Deep Research or DeepSeek or whatever, right? Isn't there a little bit of the horse is already out of the barn? I mean, like the ethical question of, am I using somebody else's information when I'm now interacting with these? they're already there, right? So I guess from a legal standpoint, it's kind of like, is there legal precedent coming out where it is saying thou shalt not use this in your design work because it was trained on somebody's proprietary information? Do we anticipate something coming out in that space? Or is that just a horse is out of the barn? It is free. Yeah, maybe we didn't do it right, but it's there. Deal with it.
Yeah.
What's your view on that?
It's a great question because there was actually a very recent ruling by a federal judge about the exact same issue that you mentioned. One of the AI companies was sued over some of the publishers because allegedly they had used a lot of their books for their AI training. And they were saying that this is an infringement on their copyrights. And the judge, the ruling was that this is not an infringement of copyrights. It's the same as saying, let's say a child is reading all your books to become very knowledgeable, and that child, when that child becomes very knowledgeable and can repeat all of those information that has already learned, it's not an infringement of copyright. It's just protected by First Amendment. So I think that part is already just in the course now, and for that specific case, the AI side won. And also in our field, I feel like there's a lot of potential in localized and offline deployment of large language models, where instead of relying on these online models, teams develop their own internal large language models, basically deploying a lot of these large language models and train those models on their own internal documents, and that takes it out of the way. So yeah, there are ways to do that, but it should be an active part of the conversation. So
Awesome. Thank you so much. Looking forward to the second half. Thank you.
of course. All right. All right, so let's get into the second half where we will be talking about two different case studies, engineering case studies. So before going there, let's just go over some definitions so we are all on the same page, and then we will get into the results. So I want to first start by talking about mechanistic models, for example, active sludge model. And it is an integral part of digital water because wastewater treatment solutions are primarily driven by biology, and you can't really take away that biology from your considerations when you're using AI. So that's where mechanistic models really shine, and they're based on basically fundamental principles, and they describe the underlying physical and biological processes. And they always require a deep understanding of whatever process is going on. You can't really expect to become an expert on mechanistic modeling if you don't have a deep knowledge of whatever process you're trying to understand. And when we're using these mechanistic models, we can use them for a variety of different reasons. There are different versions of mechanistic models, but they're generally accounting for microbial growth and decay, substrate consumption, oxygen consumption, and nutrient removal. And there are so many different platforms that allow you to deploy and develop these mechanistic models. Sumo, GPSX are two examples. There's Simba, there's BioWin, there's so many other alternatives. It just goes back to your personal preference, or in the case of consultants, to your client's preference of which platform you use. So as I'm talking about my presentation, please remind that we don't really have any specific preference over these platforms. On the other hand, we have the machine learning models where they're based on mathematical algorithms. You don't really need to have system assumptions to develop a machine learning model. To some degree you do, but the methodology is the same. If you are proficient in developing machine learning models, the methodology and the steps are pretty much the same. And physical process knowledge usually is not required. You can technically develop a machine learning model in different processes as long as you have a clearly well-defined data set, technically, but process knowledge, of course, is still valuable. And there are a lot of different kinds of machine learning models. You have it can start from a simple linear or multiple linear regression model to tree-based models or to artificial neural networks. So when it comes to deploying and developing an integrated machine learning solution in the industry, it usually comes to three different layers. The first layer is the data collection part, data cleaning part, feature engineering, and machine learning model selection. This layer, layer one, is where a lot of the academic studies focusing on, and for a good reason. A lot of these papers that are coming out of academic institutions don't really have access to live data platforms. So they stop at layer one, and most of the publications are just stop there. But when you're in the field and you want to deploy a developed machine learning model, then you need to connect your already developed model to live data platforms. And once that is done, you need to continuously monitor the performance of your machine learning model, because it's like a garden. You need to keep watering it to make sure that it stays green. Machine learning models need to be retrained after a certain period of time to make sure that their accuracy stays at the desired level. So that's layer 2. And then on layer 3, we have the integration of machine learning models with these mechanistic model platforms like Sumo GPSX, for example, to create the full-on digital twins for different plant operations. And when it comes to this, I mean, one of the surprises that you will probably face if you go into consulting after you're done with your studies is that when you're in school and you're doing your machine learning projects, it's 95% just machine learning code, But when you want to deploy these solutions in the field, you'll be surprised that maybe like 10% of your entire code base is machine learning, and 90% of it is dedicated towards the software engineering part, of like creating the connections between your live data platforms, deploying that into a cloud-based platform, all those things. So it's going to be like 90% software, 10% machine learning, and that's going to be one of the surprises that you will have when you move into these roles that you're responsible for deploying these kinds of models. So different types of modeling, as I mentioned, I think the most promising type of using AI and machine learning in digital water is to make them talk to mechanistic models, because mechanistic models are still extremely valuable. So the first way that we can use these machine learning models is to have a mechanistic model generate some data and then feed that data into a machine learning model. A classic case of that is error correction. If you are using a mechanistic model to simulate a behavior at the plant, and there's some error that you can't really account for, you can use machine learning to correct that error. The second way to using that is using machine learning data to feed into a mechanistic model. The best case of that would be soft sensors, where we are using machine learning to simulate the behavior of a certain sensor that is either not available in the real world or is a faulty sensor, and we're using machine learning that is trained on appropriate data to act as a soft sensor, and then we will feed that into a mechanistic model. And then lastly, which is the most comprehensive way of using these two together, is to have mechanistic and machine learning models talk to each other, or for example, create digital twins or process emulators, where data from a mechanistic model is fed into a machine learning model, and the data from the machine learning model is fed back into the mechanistic model. This is a full-on digital twin that so far has had the most widespread application in the field. So with that introduction, let's just go over two of the case studies that are focused on those 2 points. So the first one is going to be focused on the Hampton Roads Sanitation District Nansemond treatment plant. This is a plant that began its operation in 1983. And it treats, excuse me, just 1 second so I can log out of my Teams. I get all these messages. Okay, we're back. Yeah, so it began operation in 1983, and it treats 30 million gallons of wastewater per day. They're using a 5-stage Barton process to meet biological nutrient removal standards. And their current operation for their chlorination process is to use sodium hypochlorite. And the way that they're doing that is based on a feedback control system that tells them how much sodium hypochlorite to dose. And one of the issues here is that it's a very expensive chemical, and it goes back to our point earlier. If you use too much of it, you're going to have a lot of money wasted. If you use too little, you're risking your discharge limits. So there's always a sweet spot here. And the considerations at the plant are that they should not have no more than 36 exceptions with chlorine concentrations per month, meaning that their effluent chlorine concentrations is less than 0.5 milligrams per liter. So that's defined as an exception. And they should have no violations with chlorine concentrations less than 0.1 milligrams per liter. So that's going to be a violation, and they should have none. And the main problem statement here is to see if we can use machine learning and digital twins to minimize sodium hypochlorite usage, while also maximizing the number of times that we are meeting our parameter requirements. We do not really want to violate our parameter requirements at all. So it's just that sweet spot, and we are trying to see if digital twins can be used to achieve that goal. So as I mentioned, the feed-forward component is going to be based on the feedback component is based on a chlorine sensor that it measures the amount of chlorine that is leaving the plant, and they estimate how much sodium hypochlorite to use. And it has a lot of problems because it's a feedback control system, it's delayed, and they can't really have full control over how much chlorine they're using. But the feed-forward component that we are offering here is based on a hybrid approach where we're using a mechanistic model that is based on chlorine decay and a machine learning model to offer that feed-forward insight. So we know what our requirements are going to be in the future instead of relying on a feedback sensor. And so the first part of it is a mechanistic equation. Here we are using a parallel first order decay model for chlorine where it has two different terms. CT is the chlorine concentration after a hydrolytic retention time, HRT, in the chlorine contact tanks. C0 is the initial chlorine concentrations, and K1 and K2 are the equation constants. And using that mechanistic model and the data that we had, which was a pretty high resolution data from November 2022 to February 2024, it had a 10-minute resolution, and our data set had measurements for chlorine concentrations at time t, initial chlorine concentrations, and the HRT values. So using those data points, first we used a parameter fitting approach, which is called null-their-meet, to find the values for x, which is the fraction that gets decayed, and our equation constants. And we essentially ran this parameter fitting approach every day using the previous 2 weeks of data. So basically every new day, we have a new model that is able to tell us what are the chlorine decay considerations going on in our chlorination process using the previous 2 weeks of data. And the reason to do that is to make sure that we have an updated model. And using that, we can estimate the chlorine decay function given the fitted parameters and the recorded HRT values that we had at the plant. So these are the first set of results. The figure you see on the top are the chlorine residuals that were predicted by a mechanistic model. At first look, it looks decent, but when you take a closer look at it in the figure at the bottom, you see that although the trends are predicted relatively well using the mechanistic model, there is still an error that was observed between the measured chlorine concentrations and the values that were predicted by our mechanistic model. So we needed to take that into consideration, and that is where machine learning comes into play. Our main goal was to see if we can just use a simple mechanistic model, but we saw that there's error. So using that knowledge, we designed an approach to try to correct that error. So as I mentioned, the data that we had, it had the initial chlorine concentrations that were picked by the plant, and we had the hydraulic retention time values in chlorine contact tanks, and we had the chlorine measurements at time t. And using this parameter fitting approach, now we could back calculate the C0 concentration that needed to be chosen given the chlorine decay function based on our CT measurement. So we could basically see what C0 should have been if we wanted to reach a certain level of chlorine at time t. And using that, we can see an observed error between the recorded C0 values that the plant had historically used and the back calculated values that we were able to calculate using our fitted mechanistic model. And so that's where the machine learning came into play. That gave us access to a data set that was consisting of all these observed error rates. And we used two different advanced time series forecasting models, neural profits and transformers, to try to calculate that error. So the first one, the neural profit, it's a iteration to Facebook profit, which was introduced by Facebook. And it's a very powerful statistical model that the original one is a statistical model that is really powerful in capturing trends, seasonality, and um, the location of data points in time. The neural profit is an advanced version of that, where it allows you to combine those statistical features with neural networks. And it's a really powerful model because, like I said, it captures all the seasonality and trends, and also it allows you to take into consideration auto-regression features, which is essentially using previous values to make predictions into the future. The issue with that is that it has relatively limited scalability with large data sets. And the second part, we use transformers, which was one of the novelties of this study. Transformers are essentially the building blocks of large language models. You know, they're the building blocks that allow you to interact with large language models. So let's say you talk to a large language model and you ask it, "How are you?" It is able to differentiate that sentence with "how you are" or "you how are," for example. It knows that it doesn't make any sense to put those words in that specific order. So that's why transformers are really powerful in detecting the relative location of any value in a time series data set. And because of that feature and because of that strength in accounting for time series dynamics, we use that part. The issue with transformers is that they are really data hungry. Our study had around 60,000 data points, and it still it could have gone higher. You know, it could have gone higher to like 200, 300,000 data points to make sure that we are maximizing the performance of the model. So if you have a large enough data set, transformers are going to be an amazing tool to make sure you have a really powerful model. So using those approaches, we wanted to predict the error that the mechanistic model was giving out. And here are the results. This is the results for neural profit. Again, if you look at the top figure, it looks great. But if you take a closer look, you will see that the model has a really high predictive performance, but it has a slight delay, you know, and that delay can create issues. It can lead to inaccurate control over the chlorine concentration, and it's not ideal. You know, it's something that we don't really want. So initially we were happy, but then we realized, okay, so we need to figure it out. And so that's why when we developed the transformer model and did the same thing, you know, basically trying to predict the errors that were observed by the mechanistic model, we saw these results, which were a significant improvement over the neural profit transformer model, the neural profit model. Here we see that the transformers were able to provide very accurate measurements, very low RMSE and mean absolute error values, and also they had solved this delay problem. You know, it's just another evidence of how powerful transformers are in general. So that allowed us to correctly account for the mechanistic model errors that we developed for the chlorination part, and allowed us to provide that feed-forward insight into accurate prediction. So, and what we observed here is that this was a great example of the issues that is involved of relying only on mechanistic models sometimes, because sometimes they can't really account for certain errors, you know, and this is a great example of using machine learning to account for that error. Again, as it goes back to my earlier point that one of the most promising ways to use these types of models is to make them talk to each other, you know, want to make sure that they are complementing each other, you know. So, and we are not relying only on one source of modeling source to basically do our achievement. This was part of the Intelligent Water System Challenge that we did last year. That is Jeff Sparks. He's such a great mind in advocating these digital tools. I'm really grateful for our collaboration. And that's Amir Bagheri, one of my colleagues. If you want to access the full solution with the full details, you can access it through the Water Research Foundation website, and the solution is available there. With that, we are going to go over case study 2. I don't know if you want to take questions now or later.
Well, I'm happy to ask a couple on that
Okay.
one. So let's drill down a little bit in terms of kind of the methodological question here, right? So as I understood the way you were presenting it, essentially the kind of the machine learning, the large language, the AI, right, are doing some advanced statistical analysis to look at your data sets, right? And so the questions that we would have there is the independence of the data that's going into the data sets, right? Like the statisticians who developed what we mean by these tools had made some assumptions about the kind of data that would then be analyzed. And oftentimes in wastewater, we don't really have the same degree of independence that might go into some of the assumptions of developing some of the tools. You know, time series data from one treatment plant produces a lot of information, but the degree of independence could be somewhat argued in that. So how do you balance back and forth between knowing what's under the hood in terms of the assumptions that went into the AI tool you're using versus the kind of data and the realities of what the data is? How do you balance that back and forth as a super user, as a person working in this space?
Yeah, that's a great question. So let me actually go back to this slide because this is exactly what we're talking about here. So the first, but I think that question goes back to the data collection part and the data cleaning part and the feature engineering part in layer one. And what a lot of people need to realize is the majority of, if you're developing a machine learning model, the majority of work goes back to those questions, answering those questions. What are the characteristics of my data? How do I make my data suitable to develop a machine learning model? For example, I mean, if there's collinearity between my different features in my data set, I need to remove those features that are related to each other, because if I don't, that's going to artificially increase my prediction performance, you know? So all those, as a data scientist or AI engineer, our number one responsibility is to make sure that the data we are feeding into our machine learning models are as objective as possible, as clean as possible, and as appropriate as possible, suitable and tailored for that specific machine learning algorithm. And that creates the majority of the effort. You know, you might spend like 70 or 80% of your time just to get your data suitable for that specific machine learning model, and then 20% of your time to write the code for the actual model itself. So that's a great question, and that's probably the most time-consuming part of developing all these models.
Awesome. Thanks so much. Looking forward to
Of
the
course.
next.
Okay, so now we are going to go over the second case study, which is focused on Fond du Lac. So Fond du Lac is a wastewater treatment plant that is located north of Milwaukee, and it serves a population of 75,000 people. And they have a pending effluent phosphorus TP requirement of 0.17, which is really, really low. And that's the biggest challenge that they have. They get a lot of different contributing factors to the quality of the wastewater that is introduced to the plant, like inconsistent industrial waste streams and locally sourced waste carbon. So that creates a situation where it's very important to have some sort of AI help in determining the best operating conditions to meet those pending future effluent discharge limits. This is an overview of the treatment process at Fond du Lac. Um, they're using an anaerobic aerobic process, which is based on an ABAC system, ammonia-based aeration control. They have side stream deammonification, and they do not have any tertiary filters. And what you can see here is they're using external carbon to aid with the biological phosphorus removal, and also using ferric sulfide to trim their effluent to make sure that they are meeting their effluent discharge limits. So the focus of this study was to first develop predictive machine learning models to predict the future concentration and loads that are leaving the primary effluent using the plant's data and the weather data that we had access to. And to use those machine learning predictions of future loads and concentrations leaving primary effluent clarifiers to try to feed them into a mechanistic model or a sumo model and simulate the behavior of the plant to see how it performs under various treatment conditions, you know. So when we use all those machine learning predictions into our mechanistic model, our plant operators are able to simulate different scenarios, use different chemical concentrations, use different operating set points to make sure that the decisions that they make leads to meeting those effluent discharge limits. So basically, Here again, we are using a machine learning component that predicts future loads and concentrations, and we use those predictions to feed them into a mechanistic model to give us a full idea about how the treatment performance is going to be. There's a lot going on here, but this is the general workflow of the digital twin that we have at Fond du Lac. So this just shows us the core predictive model, which is again to simulate the secondary treatments with a one-dimensional secondary clarifier in Sumo, and that's the core, that's the heart of our digital twin. And as I mentioned, the data points that we use to do that is to first connect our system to an online rain forecast API, and also use the influent and operational data to make those machine learning predictions into the future primary effluent flows and loads, and then use that to feed them into our Sumo model. And then on the side we have a auto calibrator here, and the reason to have this here is to make sure that our effluent TSS is in range. What we realized was there was a high correlation between effluent TSS and effluent phosphorus, because a lot of the phosphorus was in particulate form. So one of the key factors here was to make sure that our total suspended solids performance and range is in range with the real data, and that allowed us to have much more accurate predictions. And then once all those things were done, we we're able to conduct scenario analysis. We're using all the operational considerations and the chemical doses that we that the plant operators wanted to choose. They do scenario analysis using this hybrid digital twin, and they see that if their effluent OP is going to be in range or not. If it's not going to be in range, they will choose a different set of operating conditions and rerun the models until they're satisfied with the effluent OP or orthophosphate that they observed in their effluent. If it is satisfied, then we visualize the data and we show the plant performance in different dashboards. And like I mentioned, once they're satisfied, they will just output the data. So here, but the one on the right, that's a Sumo model that we have developed. It's a fully calibrated mechanistic model that mimics the behavior of the plant. And then one on the left is just that 1D clarified model that we use to optimize the flocculation coefficient to make sure that our effluent TSS is in range. And to show you how important that is, the figure on the left, this light blue one that you see are the effluent TSS predictions that were made using the default RFlock values. And the squares are the real data that we had. And you see that there's a lot of discrepancy between these two streams of data here. But once we use calibrated flocculation coefficients to make those effluent TSS predictions, you can see that the data is going through all the observed data, and it leads to a much more accurate performance for accounting for effluent TSS. And here you see the impact of that auto calibration on the flocculation coefficient. The black line is just unoptimized RFlock, and the green one are the optimized ones that were done according to real conditions at the plants. So doing that, I just wanted to show you some results. First, going over the legends here, the red lines that you see are the model data, which are the Sumo predictions. The gray and the green ones are the machine learning predictions that are related to the primary effluent, and the blue ones are the real data that were recorded by the plants. So here, if you remember, since we are looking at primary effluent data here, we don't really care about the Sumo predictions here. What we care about are the machine learning predictions and making sure that they are in range with the observed data. And we can see here that, for example, for primary effluent TSS and primary effluent BOD, the machine learning models were able to provide pretty accurate predictions into the next day when we compare that to the real data that was observed at the plant, except some of these peaks, for example. That's one of the challenges with machine learning models. If your training data is not large enough, and you get sudden peaks, those peaks do not really get seen by the machine learning model, and that's something that you need to always consider. And then when we look at the effluent data here, again, since in the effluent, we are only caring about the sumo model predictions and not the machine learning model predictions here, we are only interested in comparing the red line with the blue line. And that basically allows us to mimic the performance of the plants in the future. And what we see here is that the digital twin was able to account for the performance of the plant, for example, for final effluent TSS and final effluent TP, and it did a pretty good job in accounting for those differences. Again, you see that sometimes the peaks might have some inaccuracies, but that happens. One of the good things about running these types of systems is that um, the more you run them, the more data that you have, and the more accurate that the models become. So that's a consideration. And this is a work in development still, this part. That's why I'm just showing an Excel figure. This is, again, we are using a machine learning model to try to correct for the orthophosphate predictions that were made by the sumo model. We are working on this thing to get it implemented in the overall solution too. And what you see here is the measured orthophosphates. It was sometimes different from the sumo predicted values. And one of the reasons is because the data, the range of the data is so small that even a small difference in the predicted values leads to a large percentage. But when we used a corrective machine learning model on top of these OP predictions from the sumo model, you can see that the predictions are much more accurate. So that's why, again, it shows us the importance of incorporating predictive machine learning models to make your mechanistic models more accurate. And so with that, this is still work in development. We are working on different parts of it still. But since this tool was utilized and deployed, we could observe much more stable phosphorus removal performance from the plant and facilitate the decision making that was being done at the plant with these advanced digital tools. I want to thank all my colleagues. I'm not going to name individual ones, but these are all my colleagues and collaborators from our company, Maya Water, and other facilities across the US. And this was a big team effort. So with that, I'm going to finish my presentation. Thank you all for being here and listening to me talk, and I'm happy to take any questions.
Oh, that's fantastic, Aaron. Thank you so much. This is wonderful. This is wonderful. I'm going to ask, if you don't mind, if you please will pull down the screen share, then that way people will be able to see our smiling faces. I know in Zoom they can toggle over, but it just helps folks. So we've had a lot of great questions in the chat. I've got some thoughts here together. Let me take you through kind of like an overview or an outline of what we'll talk about, and we'll come back and pick up people's questions as well as they drop them in there. But we're going to go back up and first think about some background and some motivation at the high level, right? So there was a while there when it was microbiology, then we called it environmental biotechnology and genomics, and it used to be called organic chemistry, and then we called it nanotechnology, right? Then we used to call it statistics and modeling. Now we call it AI and digital twins. So there's a little bit of greenwashing that we equate with sustainability. There's a little bit of AI washing. So we've got some questions in that background space to understand what's real and what's not, particularly if you're a utility and somebody's pitching to you. How do you tease through that? So we'll go into that for the background. The second then is like some very practical questions, right? So yeah, real-time monitoring, predictive maintenance. I mean, like all those things sound great, right? But I mean, that was great when we had SCADA and automated valves. But I mean, all it takes is, this is wastewater treatment, not chemical engineering. Some rags come through, right? Like the stuff gets torn up. So where does AI really work in terms of the operators? And, and predictive maintenance, that's awesome. But we all know it's deferred maintenance. It's how far can I push off spending that money? No matter how well you predict it, I just don't want to spend it until the thing breaks. So the balance there of and we've got some very practical questions that some of the audience put in. So we'll pick through those in that kind of very practical session. We've got a specific question that was a very kind of practical question about one of the case studies. So we'll come back and pick that up. And then a little bit about like the students, the power users, right? So you did a great job of mentioning Jason's paper. He gave a presentation here a couple of weeks ago, which was great. So if students or young professionals or folks working on degrees or other training or going back, is this the kind of stuff that you can do on your own, learn on your own, bootstrap? Imagine the scenario, you're a student, Your faculty mentor says, "Oh, I want you to bring AI into your project." And your faculty mentor knows nothing about it. You,
Yeah.
as a student, know nothing about it, but suddenly you're going to bring this in. So,
Yeah.
do they need to bring in? Do we, as a profession, need to be leveraging some relationships with others? If so, who and what? How do we make this work? Because this is a tool that is clearly very valuable and powerful.
Yeah.
How do we have the expertise to use it, and how do we acquire the expertise to be
Yeah.
able to use it? And then we'll wrap with the standard, your words of wisdom for others. And so there's a number of questions that I also see coming in, so we'll pick those up as we go along. But if you're okay with it, let's back up to the kind of the back at the high level. Let me read the specific question that's in here, and then you can kind of look at this, right? It's the terminology and the promise, right? So the question is, I think the hammer looking for a nail comment is a huge issue with all the AI buzz. As a water agency, we hear tons of pitches from tech providers and consultants, and we struggle to figure out how and whether their offer can work for us. How do we fix that issue?
Yeah. Yeah, that's a great question. And that's always one of my, in my professional life and my personal life, I always want to be completely clear about the intentions and the promises, I'm not a salesperson, A lot of these pitches that you hear are from salespeople, which I have nothing against them, but I feel like they have a tendency to over highlight the potentials and the promises and maybe undermine some of the challenges. I think if I was a water utility first, I would look at the data that we have. I always use the pizza example. If you want to have a delicious pizza, you need to have good ingredients. If you don't have good ingredients, no matter how amazing the chef is, the pizza is not going to turn out to be well made. So as a water utility, I would first look into the quality and the quantity of the data that I have. Machine learning models are data hungry. You need high quality amounts of data to develop those models, and also you need to have a continuous high quality stream of data to be able to maintain those models. So if you're a water utility, just look at the data that you have, look at the number of instruments that you have, look at the way that you are storing your data, and the potential to enhance the quality if it's possible. If it's possible, then yes, I would strongly look into digital water solutions. But if the ingredients of that pizza, if the data quality is not, and it's not like high enough, I would first focus on developing an extensive set of tools to make sure that my data quality is high enough, and then go there and look into hiring people to develop a machine learning model for me.
Garbage in, garbage out. We got it.
Exactly.
Right? We got it. Right.
Yeah.
Okay. Fantastic.
Yeah.
We just need to put hashtag Gigo on all of
Exactly.
our
Yeah. That's the best.
information, and we're in good
Yeah.
shape. Okay.
Yeah.
So let's move on then into a little bit more, we'll stay in this practical space, right? So you gave some background, like, hey, real-time monitoring and predictive maintenance, and these are some of the places where this can play a role, but then the pushback's going to come, right? Like there's SCADA and there's valves, but there's RAGs. These are wastewater treatment plants. I can put DO meters everywhere and they get ripped out. I can put automated valves and they corrode because no one exercises them,
Yeah.
right? I mean, predictive maintenance is just like guesses of when we want to spend money, but no one ever wants to spend money. So a better prediction of when to spend money. So can you point to where AI moves the needle on these things that have kind of always been promised by the next technology, the next sensor, the next SCADA improvement? And I'm using
Yeah.
SCADA broadly there, but
Yeah.
where does AI move the needle in reality on these things that are always problems, and technology kind of always seems to be, it's going to solve them for us, but they've never been solved. So
Yeah.
where does it actually move the needle on these?
I mean, AI is one thing, and also the innovations in the instrumentation part is one other thing. Sometimes I see a lot of new instruments that are coming into play that allows us to, for example, account for those rags. I don't want to go back to my PhD study, but my main PhD focus was on bioelectrochemical sensors that were actually like very powerful in detecting those rags. And I was using AI to be able to use those signals to be able to detect those rags before or before they happen. So I feel like one of the things that we can do is to first use novel instruments that are coming out, just giving them a shot. I know there's a tendency to keep using the sensors that you're comfortable with, for the past decades and not try new stuff. I would say we need for successful implementation of these things, we need to have a dedicated focus, no matter how small or large it might be, on using new innovative instrumentation tools. And when we do that, we have a much higher quality stream of data to feed into our machine learning models, and we can open new doors to us, And those predictive maintenance, I mean, it can be a wide variety of applications and topics. Let's say you have sensors that are deployed across your city, on your tunnels and whatever, when they're hard to access, you can use machine learning to do that. So there's a lot of work to be done. From what I see, I don't see enough machine learning models out there that have dedicated focus towards that, so we can talk about their failures. I only see potential of we won't know until we actually try. That's what I'm trying to say with new instruments. So
No, fair enough, fair enough, fair enough. I like that perspective. That's
yeah.
that's helpful. We've got a couple of like specific questions in here, so let me kind of read these to you, and we'll take them kind of one at a time. So, in your use of machine learning and AI, if you're making this as part of a typical presentation to an existing facility, and you're talking about employing this as best cost-effective practices for a new client and a planned upgrade or a process revision, what kind of lifetime do you use for system and hardware?
Lifetime in terms of developing these tools or using them?
Well, lifetime in terms of, like, hey, we're going to do this, we're going to put this together, right? So if you're now working in an AI world as
Yeah.
opposed to an empirical or a mechanistic engineering kind of
Yeah.
world, what would be some of the lifetime that you would use? What would be some of the rules of thumbs you might use for the system, particularly the
Yeah.
AI and the hardware? I mean, is the digital twin good
Yeah.
for, you spend all this money, you create one? I guess it's good for 6 months, because then
Yeah.
the next large ML model comes out and you're like,
Mm.
oh, and I can fit it even better. So
Mm.
so for the systems and the hardware, what are some of the lifetime
Yeah.
values?
Yeah, so I would say it's a very case-specific question. You work with certain plants that they have very robust data collection platforms, very robust data storage platforms, and if I'm working with a plant like that, the amount of time that I need to get set up with the development part of a machine learning model is going to be much shorter compared to a plant that has data in very localized storage places, and they need a lot of work to make sure that those data points are appropriate and made. So I would say before looking at I would love to answer this question, but before looking at the conditions of the data storage and data collection of the plant, I can't really uh, give like an accurate number. Let's say if it's HRSC, HRSC is an amazing facility when it comes to data storage and data collection. You can pretty much immediately get started developing your models because they have such a robust way of collecting data, Um, the machine learning development part does not really take that much time. You need some exploratory, you need to do some exploratory work. I would say that the part that takes the most amount of time is the deployment and creating all those individual data connections to your data platforms, to your cloud-based platform, and to your machine learning model. So yeah, it takes at least a few months to get set up, and make sure that the infrastructure is there. And once it's set up and running, it can, as you say, it can run forever basically, as long as you maintain your sensors and you maintain you water that garden, it can run forever. So
I love it. I love it. Another specific question for operational control elements, chemicals, flow rates, those kind of things. Can AI be configured to learn from results like effluent quality to refine control? So can you can you adjust your controls based on your outputs from your effluent quality?
oh yeah, for sure. That goes back to the part where the maintenance part, when we deploy these models, we need to continuously monitor the errors that are built into them, using, for example, those effluent data points. And there are ways that we can use those effluent data points and the errors that we have measured to go back and make our AI models more accurate. So that's one of the things about AI. The more you use it, the more data that you have, and the more accurate that they become.
Perfect, perfect. Another specific question, right? So when you design particularly industrial wastewater treatment, how do you incorporate variables that might be unique to their waste characteristics of a particular industry?
I would talk to the process experts of that specific industry. That's the part where domain specific knowledge comes into play. That's the part where if you have a pure data scientist or pure AI engineer, it's not going to be much helpful. If you have an AI engineer with domain specific knowledge, they need to sit down and talk to the designers and tell them, hey, like if we have this certain application in the future, we need to make sure that this specific part, this specific instrument gets implemented into this process. So I would say to do that, we need to make sure that domain-specific knowledge gets mixed with AI knowledge.
Perfect. Another specific question along these lines, and I'm going to read it the way it's written, but then maybe we'll talk about what it's asking as well. So over time, are you able to transition your calibration factors, presumably of your models, to reflect actual physical or biological mechanisms? And then can you incorporate those? So to me, I'm reading that as like, does AI help you learn mechanisms, which you go back and improve your mechanisms, and then so is there an iteration there between the correlations perhaps that the computer is giving you and the causations that you start to learn and understand? Can you talk about those interplays?
Exactly. That's one of the main cores of any type of digital twin solution that we offer. That specific step is going to be one of the main steps that we take when we are developing and also deploying these models. That constant calibration that needs to be taken into account, and that always happens. So it's a core piece, it always happens. We just need to make sure that the type of data that we get from these calibration efforts are appropriate for our machine learning models. As long as they're appropriate, we can always go back. It's a bit of an effort, but we can always go back, modify our models, and just make them their.
Perfect. No, makes sense. Makes sense. And then we've got one particular that came up when we were in the case studies, and this was the Fond du Lac facility is where this question popped in there. Okay, so it starts with a little bit of a statement, right? The best way to ensure more predictability for organic and hydraulic loading is equalization. So now, so given that reality, right? So this would greatly simplify the process with a rudimentary mass balance math compared to the more complex AI and all. So what are your thoughts on that? I mean, we've known that when you've got process variation, I don't need to, deal with it or model it, or I just EQ it, and my life has gotten better. So how does the balance between the practical empirical part of equalization and then the predictability and the highly fine tuning that you can do with an AI approach?
I mean, I appreciate that question, but what we need to consider is a lot of these facilities, AI is usually not their first step to take. They take all the steps that they can do, to make sure that they are doing what they want to do with all those equalization tags and all these like process variations. Especially in the case of fund, like they make sure that they have done all these steps, and if none of them are producing the results that they're interested in, and then they will go towards AI and machine learning. So I'm pretty sure in the case of fund, like all those preliminary steps have been taken, before the motivation for this study began.
So this comes out to maybe an observation, right? Is that you're saying we do good engineering, whether
Yes.
it is our
Yes.
classic chemical engineering approaches, or we do all our good engineering, and then we're using AI as
Yeah.
a complement and as an efficiency or an improvement, an extra tool in that. It's not a replacement. It's a plus up on.
Exactly. So even I should be the number one promoter of AI, but what I always also say is you need to first take all the necessary steps that you do in your typical traditional design work, in your typical modeling, mechanistic modeling. If none of those steps work, then we need to move to AI. So AI is just a piece that complements all your previous efforts to reach a certain goal. If all those previous efforts did not really reach that goal, that's when AI comes into play as a complementary factor, not as a initial factor. So.
Fair enough. Fair enough. So then in the case of that, right? So then while we imagine maybe I am a newer engineer to a team, and somebody that's more seasoned on the team says, "Well, awesome, you're here. We want to add AI into this." Or you're a grad student, or you've gone back to school, and your advisor says, "Oh, we've got this great project. I
Yeah.
want you to add AI to it because it's the next great thing. We'll get
Yeah.
it published, we'll get funding, et cetera, et cetera." What's your advice to those people? Do they need to go find somebody that knows what they're doing? Is the real effort in, it seems like for you, it's really in the quality of the data and the data science engineering part. And what would be your advice to those folks who are suddenly facing this as a challenge?
Again, it goes back to my to that why and how problem that I was talking about. For me, I may have a different perspective on this compared to a lot of other people. I need to have a really good and clear motivation to get started on AI or use AI and machine learning in my project work before learning how to do that, you know. So if that is the case, I mean, it comes pretty naturally. My personal preference is to have people who are learning AI and data science coming from a domain-specific knowledge, because it becomes a very powerful tool when you have domain-specific knowledge. For example, in our case, when you have process engineering knowledge and you learn AI on top of that, you can open a lot more doors compared to just being a pure data scientist, you know. So if you want to like get started in that field, my personal recommendation is to uh, get comfortable and get very fluent in whatever domain specific area that you are, and then learn all the data science and the AI techniques later on.
No, I appreciate that. I appreciate that. We got a couple more kind of like, specific questions before we get into the opportunity for you to kind of share some thoughts here. So, specific question, acknowledging, hey, it's not, it may not be exactly your area, but can you speak to, or are there any folks that people should go out to if they want to understand where this is being applied? Particularly thinking about groundwater models, I'm guessing there it's probably in either water production from wells, but also probably in remediation and flow through with groundwater problems. Are there groups or are there folks? I mean, your area was clearly here in primarily in the wastewater treatment space. What would be some names, or are you familiar with groups or folks they should go out, particularly in that groundwater space?
I can potentially come up with names from my graduate studies. I don't have them off the top of my head, but like whoever asked that question, please feel free to reach out to me on my email, and I'll be happy to answer that question for you. I know some research groups that are active in that area, and I'll be happy to send that through email. I don't have them off the top of my head.
No, I figured, but I thought I would ask the
Yeah.
question because it came in, and I figured you're a friendly fella, and be
Yeah.
happy to help connect people with that. We
Appreciate
had
it.
another specific question that was a little bit on the kind of like the types of data, right? So we might often think about, I go to the lab and I get some data, and then I come dump that into my model, right? And so whether we're just thinking like, the straightforward, like, well, I want to do my Streeter Phelps of my stream, so I want to know my decay coefficient. So I go in the lab and I get a BOD number, and then I come back and dump this over here. When you're talking about data, are you talking about that kind of data, or are you talking about the real-time data that's already or all of the above? I mean, is there which kind of, when you're saying data, what do you mean?
So it depends on machine learning models. Generally, they really like high frequency data, you know, and uh, generally, if you want to develop a machine learning model to make predictions, the frequency that you're interested in should be the frequency of the data that feeds into your model, even like higher frequency. So let's say if you want to make next day predictions, yes, you can use potentially like daily lab data for like a few years ago, you know. But if you want to use your machine learning model to make hourly predictions, you can't use lab data because that's not high frequent enough, you know. There's usually a rule of thumb that it says, depending on the number of features that you use to train your machine learning model, you need 10 times that number of features as a minimum number of data points to train your model. So let's say you're using 5 different variables to train a machine learning model, you need at least 50 data points. That's like not really based in reality, but like it's just you need like at least 50 data points. So it goes back to the frequency that you desire from your models. You know, if you want high frequency measurements, predictions, you need high frequency measurements.
Perfect. Perfect. Sounds great. Okay. And so now just looking to kind of wrap up, right? So we're going to, we've got seasoned professionals in here, we've got emerging professionals, we've got students, but your presentation, this topic is somewhat a little bit unique, right? Because most of us across the field, this would be somewhat of a new area. So if you could speak to perhaps those kind of three demographics, the seasoned professionals, those folks that are, what we might call as the students and young professionals, bending that into the folks that are out in practice, then the folks that are coming on as students. If we can talk to those three groups, what would be some of your advice for them in terms of how to avoid being left behind in a virtual, digital divide, but an AI divide between those that do and don't know how to use this? Students might be worried about using it too much and not learning enough, kind of that MIT study.
Yeah.
Seasoned professionals might not know it enough and might not, don't want to teach the old dog the new trick kind of thing. So when you think about those three groups, the seasoned professionals, those that are active in their career and looking for opportunities for advancement and adjustment, and then those students coming on, what advice would you give to those three different groups?
So for students, I would first strongly recommend them to find a good motivation to use AI before spending time developing robust models, because um, as a reviewer, if I see a paper that doesn't have a good motivation, I'm probably not going to recommend that for publication. You need to have a good motivation. And when you're in school, you have two different pathways. One is to First of all, you, I'm not including computer scientists. If you're a computer scientist, your goal is to come up with new algorithms, which is not what we're discussing. We're talking about applied AI here. If you're using applied AI, you have two different paths. One is to move the borders of knowledge, using AI in a very specific area that has not been used before, and you're moving that border of knowledge. And two is you are recommending using AI for some potential future industrial application. If that is the case, then you need to make sure that the motivation behind your study and your research topic has real-time applications in the field. If it doesn't have real-time application in the field and you're just using AI, it's not going to produce too much valuable work. For seasoned professionals, I'm fortunate enough to talk to a lot of them, in different conferences, in different settings. They come from a very extensive background and knowledge of traditional wastewater modeling, mechanistic models, and for a good reason. These models have been proven to work. They're so-called white box. What exactly is going on in them, and I totally understand that people feel comfortable with them. But sometimes I see sometimes like there's a little bit of resistance when it comes to like using AI and machine learning on top of those mechanistic models, because it's just something new. People still may not be fully convinced about the value that it offers. So I would just like uh, ask them to please just consider giving it a chance, in your workflows or in your projects. Give it a chance and see if it helps. Do not immediately knock it before trying it. And for regular professionals, AI is advancing so fast that it's extremely hard to keep up with like every single advancement that it happens. I would just say submit to a couple of newsletters, watch lots of YouTube videos, and become users of AI. A lot of people say that AI is going to replace human work. I don't really think that's going to happen. I think what is going to happen is people who use AI will probably have an advantage over people who don't use AI. Like I said, I use AI for my taxes, for my gym schedule, for like a lot of these different things, and it's just look at it as in a way that you have access to some very knowledgeable consultants by your side. So I would say just incorporate AI in your daily work life and do not over rely on it, but start using it and you're going to see the benefits that it has.
Fantastic. Thank you again so much for a fantastic presentation. We really
Of course.
appreciate you being here with us and sharing your expertise. We'll turn it over to Marissa to wrap it up. Thank you.
Okay. Thank you.
Okay, thanks, Dan. Thanks, everyone, for all your questions. And thank you to Ariane for sharing your knowledge with us today. We have several webinars planned in the near future, so you can go to aaes.org/events and reserve your spot. Just a reminder, if you're not yet a member and you're considering joining the Academy, please email me to discuss our membership options. For all board certified individuals, PDH certificates for this event will be sent out by the end of the week. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.
Thank you, everyone.